Hi and welcome to the video. In this one we will cover what a PID controller is. We start by looking at the three different parts and go through them to show what each of them does. In the first example we just look at the controller output without a system, because the workings of the PID controller can be explained best like this. Then I introduce the system we are using for the follow-up step, where I show you how the different parts of the PID controller affect the system. Then we close with an outlook. A PID controller is a feedback controller. You can learn what that is in my previous video. And it consists of three parts: a proportional, integral and derivative part. The resulting output of the controller is the sum of all three. As you remember from last month's video, a controller calculates the required output based on the difference between our target point and our measurement. With our controller error, the PID controller output is calculated with this equation here, or with this alternate representation. The proportional part is the first one here, the integral the second, and the derivative part the third. The representation on top has advantages when it comes to applying methods based on Bode plots. All of the parameters marked in color define how big the effect of each of the parts is. This is shown in an animation in the second part of this video. Let's first take a look at the different parts individually. We assume that this difference, the error, looks like this up here. First it is constant, then it jumps and decreases further into the negative region with a ramp. If you have a real system, any controller input will have an effect on the system and thus change the error. But for the explanation of the different parts, it is easier to leave it this way. So this here is the error we have over time. The proportional part of our controller output is equal to the error scaled with our proportional gain Kp, as you can see here. So qualitatively it looks identical. The integral part is the integral of our error over time. For the first part, our error is constant, so the integral increases linearly. Afterwards, once the error is negative again, the integrated part decreases again. Just as an example, the integral action of our controller at this point here is equal to this surface minus this surface scaled with Kp divided by Ti. Finally, the derivative part is just the mathematical derivative of our error. Since the error is constant here, it is 0. At this jump, you will have a negative impulse in the derivative part. The height of this impulse depends on the controller cycle time. Back here, where the error decreases constantly, our derivative part is constant. And if we look at the total response, it is the sum of the three components. We now know how to calculate the response of our PID controller to a known error. But the real question is what each of the parts actually does, and we look at this next. To be able to see what each part does, we need a system, so that we can apply feedback to it. We take a simple example with this mass that is held back by a spring and a damper, and we pull at the front with a force. The force is calculated with our PID controller, and the value we want to control is the position x of the mass. We want to move from a start point x is equal to 0 to an end point x is equal to 1. The parameters of our system are given here, and the dynamical representation down here. Let's now add our PID controller step by step to the system and analyze how it behaves with each added component. For the pure proportional controller first, we can see two things. First, that our mass starts to move towards our target point, oscillates, and then stops quite a bit away. Let's look at the point where it settles back here first. The force in our controller is calculated by our gain Kp times the error here. Since we have to pull against a spring, the force at this point is equal to the force acting in the spring. At the start of our movement, we accelerate with a given force, and since the mass is in motion, the momentum leads to a small overswing. The overswing decays because of our damper. Now think about what will happen if we increase our gain Kp. Pause the video quickly and think about it. Leave a comment and then continue watching. If we ramp up our KP, the settling point back here will move up closer towards the goal point. Increasing KP leads to a higher force of the controller for a given error. Since the force of the controller is in equilibrium with the force of the spring, when the system is at rest, we get closer to our desired endpoint. In addition, since we have a higher force at time t equal to 0, we also accelerate our mass quicker, and this leads to a higher overswing. As you can see, the overswing gets bigger, but we do not manage to hit our endpoint exactly. Let's turn the gain down a little bit and add the integral part next. Adding an integral part next, in addition to the proportional, if you remember, it integrates the error up over time. So if we have a constant error over time, our force will start to ramp up. Let's now turn up the integral part a little bit to see this. I left the pure PID-Controller response in the background here just for comparison. You can see how our mass is pulled towards the final position over time, and that our oscillation gets bigger as well in front here. We can now increase the gain by decreasing the time ti, and we see that we manage to hit our endpoint fairly quickly, but we also swing over quite a bit. While the integrator helps us to reduce the error, it also increases our oscillation and introduces a risk of instability. If we turn the integrator up too much, like shown here, the oscillation takes quite some time to subside. Let's reduce the integral part a bit and finally add the derivative part. The derivative part can act like an additional damping element in our system. Increasing it will increase the damping and thus reduce the overswing, as you can see here. With this one you have to be extremely careful, however, because if you take effects like the controller cycle time and the limited resolution of the measurement into account, it can behave quite destabilizing. But as long as you do not turn up the derivative too high, it will have a damping effect like you see here. So to very quickly go through the three parts again and look at the animations. Increasing our proportional part decreases the error but increases the oscillation. Increases the integral part helps to reduce the residual error but at the risk of reducing instability. Increasing the derivative part introduces damping to reduce the overswing. Okay, and that's it already. Bit more on the theoretical side. In the next video we will look at some code and how the PID-Controller can be implemented on a real system. We will take effects like the controller cycle time and measurement resolution into account to show some of the problems you can have. Thank you very much for watching. Like, comment, share and subscribe. Bye for now.